Hello and welcome to this explanation of the complex interpretation of the geochemical and lineament analysis completed by our company on Las Animas project in Ibagué, Colombia. I should start by saying that usually the lineament analysis is the first step in the exploration of an area because it will define the most prospective area to have a volume where the deposit can be found. In this case, we started with a previous existing geochemical survey done by the government of Colombia, and I did the interpretation of that data set, found out new targets which immediately were applied as licenses by the company, and the staff of sector started to do more stream sediments in these new targets. By the time we got the results, the company decided to do the lineament analysis. So in this case, we have some geochemical data before, then we did a complex interpretation of the lineament, including the results of the geochemical data. All this will be explained in more detail in the 43-101 that hopefully will be ready by the end of this month. I'm going to be showing here is the explanation of how we got to our results. And we start with the analysis or study of the stream sediments. All these tables, of course, will be in the share folder that the company has on OneDrive. So, as you can see here is the table of content. The first tab is the raw data. Okay, that consists with the coordinates, the weight of each sample, and the results in all sorts of units, percentage, part per million, part per billion, etc. The first step was to verify the coordinates. To do this, we just select the column X, Y, and then we make a graphic, insert graphics, and as you can see, these are the results of the sampling, and the local staff confirmed that yes, this is where they took the sample. Then we deal with the data that is below the detection limit. And in this case, what I do usually, instead of putting the half of the limit of significance of the lab, I use the next significant value. For example, if the below detection limit value was less than 0.1, I will use 0.09. If it was less than 4, I would use 3. The next step was to convert everything to 1 unit, part per million. So we will work with part per millions all the way around. By the way, you can go back and forward with these links here. So here it takes you back to the table of content, and then you can just jump back to where you want to be. We use compositional data analysis to explore this data. So one of the necessity of the compositional data analysis is to have an extra column that is called the rest. And it means that we sum all our trace elements and take that amount from 100, and that will be the rest. It's important to have that column. Next, we normalize all our data by the weight of each sample. It's a good practice to do this thing. We then organize our data in alphabetic order. It's just a easy way to find the elements when we need to order them to do the compositional data analysis, which requires that we group elements in these sequences. For example, the oxidation suite, which is usually the gold deposit, will have the arsenic on gold, bronze, chlor, mercury, etc. Base metal will be cobalt, copper, nickel, lead, zinc. So as you can see here in different colors are all these groups of elements. The next step, we normalize everything by iron and manganese, which is a very good practice because both these elements, manganese and iron, when they form, they generate a huge redox environment, and any cation that will be close by, it will precipitate. So you can have an anomaly that is chemical, but not geological. So it is always very good to normalize your data by manganese and iron to eliminate the effect of these two elements. Next, we determine the erosional level. Again, a technique used very frequently in Europe, in the former Soviet Union, and it's based on the fact that there are always a group of elements that will tend to form above the ore body. They are called supra elements. And there will be a group of elements that form below the ore body, and of course they will be called infra elements. So if you have a coefficient of the supra element over the infra elements, if you have a value that is very large, that means that the erosional level is up here. This is the best case scenario because all the complete ore body is still untouched. If you get a value that is very small or even negative, that means that even though that you have an anomaly, this is a residual anomaly. It has been eroded completely. So you don't waste your time exploring this place. If you got a value around 1, then the ore body has been partially eroded, which could be an advantage for mapping because you will be seeing the mineralization on surface. So very important technique that should always be done. Then we converted the value to do the compositional data analysis. And before doing the compositional data analysis, I used a machine learning technique called Rapid Miner, which allowed me, among many other things, to reduce the amount of elements. It determines which elements are the ones that are informative. Then I use those reduced elements for the compositional data analysis. Here we have a tab with the classical statistics and the CODA statistics. I have explained many times. All the geochemical data is closed in the sense they are estimated on the basis of a percentage or a part per billions or part per million, etc. That means that they are closed, they are not open. We cannot apply normal statistical methods to closed data. And that is why it's so important to use compositional data analysis, especially when we are doing correlation analysis and factor analysis. One of the most interesting graphics that we can get is the CLR biplot, in which, again, the most important elements are the ones that have the longest axis. Compositional data analysis is a graphical statistics. We are used to tables and numbers in normal statistics. Compositional data analysis will give you the tables too, of course, but it also gives you graphical representation that are very easy to identify. So here we know that copper, mercury, and gold are the most informative elements. If two elements are in a straight line, that means that there is no correlation between them. If there are angles between them, that means that there is very good correlation. So there is a very good correlation between mercury and gold, for example. Elements that are together contain the same amount of information, so you can just pick one and don't use the rest. The principal component plot also gives you a lot of information about how the different elements behave. We have here the 4 main elements are silicon, gold, mercury, and copper. Very indicative of a granitic environment. Then we have the dendrograms. Again, very important in order to interpret the geology. And we can see here that we have two groups, the gold and arsenicum, one group, mercury and boron, that are related to molybdenum, copper, and gallium. So we have these two big groups of mineralization. One of the most interesting things that composition and data analysis give us is what is called the atypicality index. What it does, it takes each sample and compare to the next one, not element by element, but by the combination of elements. These samples here that has an atypicality index above 0.95 are points that differ completely from the rest of your data set. They are usually the indication of a mineralized point. So all these points here are very promising for as a source of mineralization. Compositional data analysis have three methods of opening the closed data, and I usually explain this as imagine the globe, Earth, and a projection, the Mercator projection on a surface. So compositional data analysis does something like that. It takes the closed data and convert it to open data. And once they are open, now you can use your normal statistical method, Excel, SysStat, whatever you want to use. There are three methods to convert the data from closed to open. These are the ALR, the CLR, and the ILR, which is the best by far, and I will explain you why. So this is how the ILR data converted looks like. This is the ALR correlation, and we are only using strong correlations. So these are, for example, there is a strong correlation between gallium and germanium, between germanium and hafnium. Of course, these are all rare earth elements, and usually they have very strong correlations. Most important, we do the factor analysis for the ALR. And the factor analysis, in this case, it found three factors, of which only factor number 3 is related to the mineralization. And the way you work with this is very simple. You just click on the factor and then you organize your sample from the strongest to the less strong. So here you see there is a big difference between 0.78 and 0.73. So I've stopped here. And at the bottom, there is nothing. Everything is the same. So this factor is basically the rare earth elements. The next factor, if I do the same, I do have calcium, sodium, titanium, magnesium on top of arsenicum. Okay, but the one that works the best, as I mentioned, is factor 3, where we have arsenicum, gold, mercury, and copper, and there is nothing below. So our first factor, factor 1 in geochemistry, is arsenicum plus gold plus mercury plus copper. This is classical of a porphyritic environment. This is how the data look for CLR. This is the CLR correlations, and the factor CLR. We got three factors that contain mineralization. Factor 2 is gold plus thallium divided by tiberium plus yttrium. Arsenicum, mercury, gold. This is similar to the previous one, divided by magnesium and calcium. This is very interesting. Magnesium and calcium, they are both plagoclast. So that is telling you that something happened to the plagoclast, we get enrichment of gold. And we also have factor 6, which is gold plus sodium, divided by molybdenum by phosphorus. Again, this is telling me that there is a process of alkali metasomatism. The ELR is the only method where you can put geological information before you do the processing. This will take too much time to explain, but your staff have already been trained on this, so they know how to do this. And at the end, you get maps for oxidation, which means the gold, base metal, chalcophile, high field strength element, rare earth element, litho, and Meyer elements. When we do the correlations, we have a good correlation between oxide plus BMC, base metal chalcophile, and there is another one which is base metal chalcophile plus Meyer. Apparently, we have two types of mineralization in the area. One is definitely gold, the other one is gold with base metals. The factor analysis of the ELR didn't give any new information. Another technique that I explained to the staff is how to convert the different values that have different magnitudes and order of magnitude into quartiles. And the way of doing this thing is I determine which is the second and third quartile of each parameter. And then if the actual value is bigger than the third quartile, I will add a value of 5. If it is bigger than the second quartile, I will add a value of 4, and if it is less, it's of 3. So for example, here, 5 means the actual value of the activity was bigger than the third quartile. Okay, and then we have at the end, we will sum all the parameters. For example, for gold, we will sum from P4 to X4. And because there are 9 elements, the maximum value that this parameter can have is 45, because 9 by 5, 45. So I do the sum, multiply by 100, and divide by 45. And this 73 is a percentage. This means that there is a 73% of probability that this value of gold, total gold quartile, is the correct one. This is a very easy way to group all these different parameters into just a few columns. And then we have all this data prepared to do maps with Surfer, and we obtain all our anomalies. So we are going to be doing now is we're going to go to the Las Animas lineament analysis. Okay, so similar table. This is how all the lineaments looks like, and we have two set of similar data. One is the actual data, and the other one is the weighted value. What is weighted? Because sometimes in our experience, for example, the main lineament have more importance than the secondary. So we will add a coefficient that we will multiply to the original values in order to get the weighted values. So we have main, secondary, tertiary, all mains, and then intersection of the main with the main with the secondary, main with the third, tertiary, etc., 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 etc. The amount of all the intersection, and the same things for the weighted value. We also did, again, using RapidMiner, machine learning technique, we analyze the clusters by two methods, the k-means and the x-means for each of these lineaments. So this is the lineament analysis. The next step is all the data, including the geochemical and the lineament. One thing that I need to explain here is how we get the coordinates equal for everybody. And for that, we use Surfer. And in Surfer, we start always by doing a variogram, because the variogram is what will give us the anisotropy, the orientation of our anomalies. So let's say we're going to do a new variogram. And I'm going to open any table. I go to Surfer. And I select whatever element, column D. And I will get the variogram. I will not explain you now how to do the processing of the diagram in order to get a better line. We just go directly here to grid data. We select green, we select the same table that we were using, we select surfer, we select column D, and click next. And then we get the diagram in order to get a better line here. We skip to the end because here is what I wanted to show you. In this point here, I will establish the amount of lines and columns for my group of data. And I always start with the most abundant data, which is usually the lineaments, and see how many lines and columns I have. So I know that it's 180. And then I will fix the maximum and minimum value for X and for Y, for UTM East and for UTM North. This way, when I click finish, my data, it will generate a grid data that has exactly 8,000 values, which is what we see here in our data here. 8,004 because I have 4 lines here extras. Okay, so that is how we get all with the same amount of lines and the same coordinates. I did the factor analysis for all. And again, we got several factors that were important from the point of view of the combined interpretation of lineaments and geochemistry. I will show you all these factors a little bit later. I did several similar things only for the lineaments and the factors for the lineaments. And again, I got 3, 4, all very important factors. And since I'm talking about this factor, let's open Word, what these factors are. In this case, it has been really, really interesting that certain type of lineaments are associated with certain type of deposit. For example, the main lineaments and the circular lineaments are definitely associated with the gold of orogenic origin, while the tertiary and the secondary are associated with the igneous type of mineralization, or also the gold that has base metal components. So, for example, factor 1 was main plus main weighted plus main weighted plus all the intersection weighted divided by the plastic K-means plus the total gold quartile plus the quartile of igneous. And here you have all the factors that we will be using in Surfer. At the end, since some of these are all gold orogenic and other are all gold igneous, I created 2 extra factors, factor 11, which is the sum of all the factors that are related to the gold orogenic, and factor 12, which are all the factors related to the gold igneous. So the last tables are related to preparing the data for Surfer, again using all the quartiles, and this is the final table that we'll be using to produce our Surfer maps. And now I'm going to show you all the intermediate maps and the final map with the targets for Las Animas. All these maps are going to be presented in the National Intel 43 101 report, and I should add that you will receive also a preliminary report just on the lineament that Dr. Vadim Galkin completed. So this is the first map. It's like a base map with the location of all the license, and in red here are the roads, just to show that there is good access to the majority of the property. The next map is the map showing you the main in blue, the secondary in green, and in red, circular reds, are the circular structures. on a base of a Google Earth map. And just to show you the detail of the work completed, these are the tertiary anomalies. Difference here is a main anomaly is above 10 kilometers in length, secondary is between 1 and 10, and tertiary is less than 1. And you must understand that all these lineaments are done by hand. There is no computer that can do this kind of detailed work. And the way my colleague, Dr. Kalkin, works, he starts with a tertiary. When the tertiary gets together, it forms secondary. When the secondary gets together, it can form a first level or main anomaly. This is the base for the geology. And this is a combination of the geology with the main and circular structures, which, as I mentioned, are the ones that are controlling the main gold orogenic mineralization. This one is the elastic three-dimensional modeling. And I want to remind you that elastic and plastic modeling, which are representative of the stress and strain of the rock, will determine where in your area exists condition to form a volume. Without a volume, there is no interest in continuing exploration. You may have the best geochemical anomaly on surface, and if you don't have a volume below it, it's an erosional anomaly. So you don't waste your time exploring there. So basically, you can see here some alignments in this elastic, and the next one will be the plastic, which is a little bit more complex, but you can also see the association with the main lineaments, which are, as I said, one of the big controllers of the mineralization. This is a combination of plastic and elastic. Basically, I could have stopped with this map here and telling you, okay, within the limits of this anomaly is where you need to conduct your further exploration. There is no need to explore around these places here. There is no potential for a volume. But because we do have the chemical data, we can combine now all our lineaments, all our plastic and elastic deformation with the geochemical factors that we determined during our study. So this one is factor 1, and this is factor 1 quartile above the 75%. And you need to remember here, factor 1, so that is the big area of potential for F1Q. I'm going to go quicker with all the other ones because what we want to see is the last one, the last two. So this is for F2Q, F4Q, F5Q. Here is interesting. This is very interesting. This is F6Q. And when we go to factor analysis, we can see that this is probably an igneous type and is clearly showing a different distribution, expanding to this area here and a little bit here. It's avoiding the orogenic type. That is F7, that is F8, that is F9, that is F10. Now, remember that I told you that I created the F11, which is a combination of all the potential gold orogenic. So this is the two types of gold that we find in the area. We have one here, which is the orogenic, and we have these ones here that is probably something related to igneous and with the influence of a base metal component. And the F19 is the best targets in general. that is a combination. This is the final map. This is a combination of everything. Our best goal targets with our best lineaments targets with the maps of elastic and plastic deformation. So to put it, simplify areas so you can see it better, I took out all the geology, etc. So this is your secret weapon at this moment. In these shaded forms are all the places where you need to continue the exploration efforts and nowhere else. Why? Because as you probably noticed, during the geochemical interpretation, we had some very nice geochemical anomaly down here, but as you can see, there are no volumes here. So this was just an eroded anomaly, probably coming from somewhere. We don't need to explore it. We only need to concentrate our exploration efforts within the shaded area. And it also is a good map, and I always stress the thing, this is a secret map. This is your secret map until you finish applying for all the license, or you try to negotiate with owners of license. I have been told by Yadiras that, for example, this part here, which is very interesting, belongs to somebody else. So I recommend you try to acquire it. We have this place here that we need to apply. This one is already covered. We have this one here that we should apply. Now, the next work to be done here is to identify these areas and do a combination of soil sampling using enzyme leach, geological mapping, geophysics using our phones, if we want to save some money. And the objective will be to define already trenches and drilling targets for all these areas here. As you can see, the mine falls perfectly well within the areas of potential. And here you can do a lot of work too. If the area to cover is too big, for example, we should not do soil geochemistry to roll this area here. We can start doing some stream sediment using the condom technique and define smaller targets. As I understand that is the city, but in other maps, we already talked about the potential of the gold mineralization extending to the east of the town. Well, with this, we finished the explanation of the interpretation. It's a complex interpretation of lineament plus geochemistry. Results are really amazing, very, very good results. And we need to get those licenses and start planning the soil sampling and mapping and geophysics to cover the most prospective area with objective of determining targets for trenching and drilling. All this will be included in the National Inter 43-101 with all the maps, etc. But I will be also sending you with this video a preliminary report that Dr. Galkin completed for me just on the basis of the lineament, just for you to get a better understanding of the work. Thank you for your attention, and if you have any doubts, you know how to contact me. Have a good day.